Good.
So today we're going to look at electron configurations again. We must always ask ourselves, what do these things represent? Because I could say to you, the electron configuration for helium is 1s2. Now, that's great that you can tell me electron configuration for helium is 1s2. Let's actually write that down. Helium is 1s2. But what does that mean? So what does this number out in front right here mean? This means the energy level. And then you would ask the question, well, what is meant by the energy level? Well, it is exactly what it sounds like. It's how much energy that the electrons have that are there. Now, what's interesting is, does the electron always have to have the same amount of energy? And the answer is no. Objects can gain energy, they can lose energy. It's true of anything. So electrons are no different than any other particle. So that means when we say the electron configuration for helium is 1s2, that doesn't always mean that the electrons are in the first energy level. They can be in the second energy level. Matter of fact, for hydrogen, which the electron configuration is 1s1, the probability that the electron is in that first energy level and an S-shaped sublevel is 90%. So all the stuff that we're giving you has got a certain degree of probability to it. So all those questions that you did on Friday, well, I guess it wasn't all that. It was only 5. The 5 electron configurations that you did on Friday, those things aren't set in stone. That's just what where the electrons are going to be occupying most of the time. So that's what these things are basically probabilities of finding electrons in those different energy levels. Now, what's the S represent? Well, that's the energy sublevel. And when you guys got your homework assignment back, make sure that you guys look at this, because some of you wrote down for this that the energy sublevel is the shape of the volume of the electron. And then you're going to see an X and it's going to say -1. The energy sublevel is not the shape of an electron. It's the shape of the volume that the electron could be distributed in. There's a difference. So you delete a few words, then you change the meaning of the whole thing. This is not the shape of an electron. So it's the shape of the volume where the electron is distributed at. For the S, what's the volume shape where the electron could be moving around? It's spherical shape. And then the P was the dumbbell shape, the D was a more complicated shape, and the F was a more complicated shape than that. Okay? And then, so that's the energy sublevel, and then what's this right here? That's just the number of electrons that are in that specific sublevel and that specific energy level. Now, where can we easily get these energy levels and sublevels, these quantum numbers from? The periodic table. So, for example, when I said that helium is 1s2, all we do is we look at the row number. The row number is the energy level. So, and then to get the sublevel, you just basically look at the bracket. So it's 1s1, 1s2. Helium's kind of interesting because for its electron configuration, it should really be in this blank spot. Notice that the P sublevel actually goes underneath the helium. So helium's 1s2. And then we just basically build up from there. So let's give an example of something maybe a little bit larger like zinc. Zinc, its atomic number is 30. So it's got, when it's neutral, 30 protons and 30 electrons. And we always start with hydrogen. And hydrogen starts out as 1s1. And then you go over to helium, that's 1s2. Now that energy level and sublevel is what? It's filled up. So when it's filled up, you can't hold any more in there, electrons. So then that's when we go ahead and we write it down. And that's why I wrote down 1s2. You can't hold any more in the first energy level in the S-shaped sublevel. By the way, we asked you guys last week why certain energy levels only hold so many electrons, why the sublevels only hold so many electrons. Remember, electrons are negatively charged. They repel each other. the n equals 1 energy level is smaller than the n equals 2 energy level. So you can only hold so many repulsive things in there. N equals 6 is a much larger space, so it can hold more things that repel each other. It's actually fairly simple when you think about things that way. So 1s2 would put us right here at helium, and then when we look at the lithium, that would be what energy level? 2. We just look at the row number. So it'd be 2s1, 2s2. That energy level and sublevel are filled up. So I write it down, 2s2. After beryllium at atomic number 4 comes boron, which is atomic number 5. So that would be 2. So now we're in sublevel P, so 2p, 1, 2, 3, 4, 5, 6. The P sublevel is filled up. So as I move out, I write it down. After 10 comes 11, so that would be n equals 3, so 3s1, 3s2, it's filled up. I'm going to write it down. So right now over here we've got the electron configuration so far of magnesium. Well, after 12 comes 13, so that would be 3p1, 2, 3, 4, 5, 6. That sublevel is filled up, that would be 3p6. After argon comes potassium, and that would be n equals 4 energy level, so it would be 4s1, 4s2 for the calcium. That energy level and sublevel is filled up, so I write it down, 4s2. After 20 comes 21, and remember we're going all the way over to make zinc, so we want to go over to here. Now when you get to the D, what do? We subtract 1 from the row number for the energy level. So this is actually 3D1. So 3D1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3D10, and then that would be the electron configuration for zinc. Now let's say we want to go ahead and do the electron configuration for germanium. We just build up from what the zinc is. So it's the exact same thing as the zinc, 3D10. And now we're still in row 4. So it's going to be 4p1, 4p2. That's right where you want to be at. That would be the electron configuration for germanium right there. Now, we're going to teach you guys something right now that's going to be a little bit different. It's going to make life easier. These electrons right here, and this right here, these electrons are not involved in chemical bonding because they're in the interior. Which electrons are involved in chemical bonding? The ones in the outermost energy level. So let's write that down. Electrons in the outermost energy level are the ones involved in chemical bonds and chemical reactions. So basically those are the important ones. What's the outermost energy level in germanium? It's the n equals 4. That's the outermost energy level for germanium. So those are the electrons that are really important to us. So for germanium, germanium has 4 electrons in its outermost energy level. And then, like we do a lot of times in science, we give names to things. Electrons in the outermost energy level are called valence electrons. So, true or false? Valence electrons are the electrons involved in chemical bonding. True or false?
True.
True. Okay. So these are the really important electrons. These other ones, when it comes time to discussing chemical reactions and chemical bonding, we can ignore them because they're just there. Does that make sense? Okay, so here's what we do to give a nice shorthand of the electron configuration for germanium, and it will be acceptable for you guys to do this on test. By the way, what do you guys know about the noble gases? Reactive or unreactive? They're unreactive. They're stable. They're filled up with electrons in their outermost energy levels. So they're not involved very much at all in chemical reactions and chemical bonds. So what we do for germanium, to do the shorthand, is germanium is basically the electron configuration of argon and every electron thereafter, right? So what we do for the electron configuration for germanium is we write down brackets argon, and what that means is write down the electron configuration for argon and then build up after that. So for argon, you're going to build up after that. That would be 4s2, then it would be 3d10, and then 4p2. So we'd write down 4s2, 3d10, 4p2, and instead of writing all of this down for the electron configuration for germanium, it's actually acceptable to write this down because it's going to be the electrons here and here that are involved in the chemical bonding and the chemical reactions. And there's going to be 4 of them that are involved in that. Do you guys have any questions with it? By the way, just because he's recording this doesn't mean that you guys can't ask questions. So, does anyone have any questions with what we've done? Yes or no?
No.
Yes.
You go beyond 1154, you write neon, and then bam.
Yeah, there's, okay, for example, let's say we want to do, I don't know if it was your class or another class, I had them do barium. Barium's electron configuration to write out should go nice and quick. And the reason for that is because barium is awfully close to a noble gas. So let's actually get a little bit of practice here. I want to write out the configuration for barium. What am I going to put in brackets? We're going to put Xeon in brackets because the rule is whatever element you're doing the electron configuration for, you just use the previous noble gas for it. So the previous noble gas for 56 would be 54. So that would be Xe brackets. That means electron configuration of Xeon. And then what are we going to put after that for barium?
6s2.
What was that? 6s2. So this is the electron configuration for barium. Is that going to save you a lot of time? Yes.
Yeah.
Okay. By the way, you guys might remember this. All this stuff is tied together. In Chapter 7, we had to learn about ionic compounds. And that was what? A metal with a nonmetal. And we said, what was the charge of barium, if you remember? +2. Remember we said we looked at nitrogen. Nitrogen tended to be -3 when it formed an ion or charged atom. So -3 for these guys, -2 for your oxygen sulfur. Your halogens tend to be -1. They tend to be 0 because they don't need to gain or lose any electrons. Your alkali metals and hydrogen tend to be +1 because they're going to lose 1 electron, end up looking like the noble gases. Well, we said your alkali metals, beryllium, magnesium, calcium, strontium, barium, and radium, these are all have a tendency to be +2. But why? Because when barium loses 2 electrons, it ends up looking like Xeon. And I mean, you can think about it this way. Here's your 6 energy level. It's got the 2 electrons in it. What happens if you lose these 2 electrons? What are you left with? The electron configuration for Xeon, yes? So you can actually look at it from that perspective as well. But yeah, this would be the electron configuration for barium. And then students will sometimes say, well, what happens if my teacher asked me for the electron configuration of a noble gas? Let's say somebody said, what's the electron configuration for Xeon? It still follows the same rules. So what's the previous noble gas for this noble gas? Krypton. So you would write down krypton in brackets. That means, again, electron configuration of krypton. And then you build up after that. So then we have our 5s2, then we'd have our 4d10, and then we'd have our 5p6.